All right, welcome to day 13 of 30 days of machine learning. It has been an exciting 12 days that have gone by. Okay, so we have got 12 very solid, very good models, all of them covering like tons of good concepts. Okay, we had PCA on day 12, and I think I mentioned at the end of the PCA video that on day 13 we have the autoencoders, and we are going to try and study them from scratch in the most intuitive manner possible, because the autoencoders are very closely related to the concept that we studied in the PCA. Now, before moving forward, one thing that I would definitely try to recommend is that if you have not watched the PCA video, or if you are not familiar about PCA in any way at all, if you've not studied the PCA from anywhere, like you're hearing the words PCA for the first time, I would definitely recommend that first you go and check out the video on day 12. That is like a prerequisite for this video, because you will see why it is. Those who have studied the PCA at least once before will see it, because the PCA is very closely related to what we are going to try to do now. Okay, so now after you have watched the video, you can come back to this one, and yeah, this video is not going anywhere. Okay, so now let's go on without wasting any time to our problem today. Okay, so what do we have on our hands today? So this is the repo. I have attached the link of the repo in the description, along with the model that we have built with the code. We will discuss everything in absolute detail later, but right now let's just move on. Okay, so if I go scroll down, this is how the repo will look like. So let's quickly read the problem. What's the problem that we'll have today? So we have the MNIST data. Okay, the MNIST handwritten digit data. So this is one of the very classical machine learning data sets available out there. Okay, so it's nothing but it's like a black image, and it has different digits in it. Let me quickly show it to you. This is how the MNIST dataset looks like. This is like one sample image. Okay, it has got 28 features here on the row, and 28 features here on the column. Okay, so like a 28 into 28 image. Okay, and see, you can see this is, I think this is a 5 here. It's very blurred, but this is a 5, and rest of this entire space is black. So this is like an example of one image that exists in the MNIST dataset. Okay, and in the entire dataset 60,000 such images exist. Okay, this is like basic data knowledge that I'm trying to give you before we move on to the problem. Okay, now what's the problem asking us? The problem is saying that of course we have a 28 by 28 image. Now when we multiply 28 by 28, we get 784. Okay, so do we actually require 784 of the pixels in the image to represent it? I think not. That is what brings us to our problem today. Okay, so let me quickly get back to the board so that we can visualize everything very clearly. Okay, so let's say this box right here. Oh, sorry, I'll make it using the square. That way it is way better. Okay, where are the shapes? No, I need the shapes here. Just a second. Hmm. How are the shapes in here? Yeah, I don't understand. Where are the shapes? This one, this one, this one. अरे यार shape ही नहीं मिल रहे. चलो कोई नहीं. Don't worry. Okay. So let me try and make the image. Okay. So let's say that this is the image, like one of the examples that we are dealing with. I'm drawing them as an example so that everything is understandable clearly. So let's say we have this 5 number here. Okay, in the MNIST data set. Okay, sure. Okay, that's fine, understandable till now. Now what is given in the problem itself is that there are 28 rows here. So we can say that this row is basically like 28. Okay, and so is this column. Okay, so as we know, each image, like any image that you capture with your phone, your camera, whatever, it has got pixels in it, right? And we that is how basically we decide the image quality. Okay, the more pixels there are in it, and when we like zoom the picture too much, you can even see the each individual pixel. So when I write this 28 here, it basically means that it has got 28 such pixels like this along the row, okay, and it has got 28 pixels along the column as well, okay. So I'm just trying to give you an idea as to how our data set looks like, because people think that this 28 is the length and the breadth. This is not the length and the breadth. 28 and 28 are the pixels which are along the row side and the column side for each image, okay. Now, okay, till fine, okay, what's the problem now? Okay, we have an image, but what's the issue? See, the issue is if I want to calculate the total pixels, okay, meaning that let me take this highlighter here, this yellow highlighter, okay, look carefully. So if I'm talking about this, what is this, yeah? Okay, so if I'm talking about this entire area, what's happening here? Shit, it's not working. Leave it. Okay, so let's say if I'm talking about, this entire area, this area, the entire area, and I ask you that how many pixels are going to be there, it's very easy. You'll say, okay, we have got 28 pixels on the row and we have got 28 pixels on the column. So we can easily say that we have got nothing but 28 multiplied by 28 pixels in total, right? Very intuitive, very simple, simple math. So it is going to be nothing but 784 pixels in total, okay. So I can say that my image, my entire image, any one image in the MNIST dataset is being represented with 784 different pixels, okay. Now comes the problem, okay. This was very important to understand so that you don't confuse this 28 with the row and column, okay. Now comes the major problem. Now comes the main thing that we need to talk about. What is the problem here? Now, if I ask you like a very simple question, and this will relate to the video on day 12 as well about the PCA, it's very intuitive. Do we need all 784 pixels to represent the data? Okay. What I'm asking is that I've got all different 784 pixel values for this image, this 5 image right here. The point is, do I need all 784 of them? The answer is no. Okay. It's a very observable answer, if I may say. Okay, so let me change the pen color to show this to you. Okay, so I've taken green here to show this to you. Okay, so can you see this space right here? Okay, first let me erase this red lines. Okay, do you see this space right here that I am trying to color or trying to fill with green? Do you see all this space here, all this space? What's all this space representing? The green space that I've tried to shade, is this green space representing something? No, the answer is no. Simple answer, no. The green space is empty. See, this is the entire image, any one image in the MNIST dataset that I'm talking about, and this area, all this empty area is basically, I can say this is useless to me. Okay, I can say that this area is useless to me because it is not capturing the information that I want. Where is the information that I want? Where is it being captured? Nothing. It is being captured by this 5 here. Now, will I need 784 different pixels to capture the value of this 5? The answer is no, because 5 is being captured by, I don't know, very less pixels, some value which is far less than 784, right? Do you understand this? What I'm saying is that this green space, all this green space that I've colored, this is empty space. Okay, I don't want this space, I don't care about this space. I care about the information that the image is carrying, and that information can be represented by very less pixels. So what am I doing with these 784 pixels? That is the problem that we have on today. Okay, the point is we do not care about these 784 pixels. They are not doing anything for us, so we try and we get rid of them. Okay, now how do we do that? How do we move forward? So very simple. So what we do here is that first of all, we get to this. Can we say that we need to maybe reduce the pixels in our dataset? We can say that, right? We can reduce the pixels of each image because we definitely don't need 784. Most of the pixels are going to be empty pixels or black pixels. I don't want them. I only want the useful ones. Okay, so if I quickly show this to you in the repo as well, let me open the repo to show you the image once again. So if you scroll down in the repo, you can see this sample image. Okay, so you see how the value of 5 is very blur. This is because these are all individual pixels. Now do you see this black space right here? Do you think this black space is useful in training any model or in doing anything? The answer is no. It is not carrying any underlying pattern. It is not carrying any useful information. I don't want this black space. So what I'm saying is that all of the pixels which are representing the black space, I can ignore them. I don't want them. Which means, coming back to the board, which means that the number of pixels that I'm actually required to represent my image is going to be very, very less compared to this 784 value. So can we say our problem now becomes something like, we need to reduce the pixels, right? We can say that. And each pixel is doing nothing. It is like representing a feature in the image, right? Each pixel is capturing some data in the image. That data might be there, that data might not be there. Okay, so can we say like we need to maybe reduce features in the image, right? Because not all of them are useful. We want only the useful ones. And when we say features, what did I tell you in the PCA video? Whenever we talk about features in terms of machine learning, we mean dimensions. Why? Because every dimension is basically used to represent a feature in the geometric space. Okay, so we can write this like, maybe reduce nothing but the dimensions. Okay, reduce the dimensions. Okay, so you see, it's been a very simple discussion till now. We discussed that how does each image in the MNIST dataset look like, and why most of the space is wasted. So we need to reduce the pixels, which we can say we need to reduce the features, because the pixels are representing nothing but the features, and the features are represented by each dimension. So this basically is boiling down to a dimensionality reduction problem. Okay, do you understand? We need to reduce the pixels, which means we need to reduce the dimensions. So we can say that very intuitively, this is boiling down to a dimensionality reduction problem. Okay, now, straight away, whenever you hear dimensionality reduction, the first thing that should come to your mind, if you have seen the video on day 12, or if you have ever studied principal component analysis, the number one thing that comes to your mind is principal component analysis for dimensionality reduction. Okay, so PCA, I explained the algorithm very intuitively. Okay, there is the entire math derivation done on the video on day 12. I mean, even when I have to revise PCA myself, I watch like my own video because I like that explanation a lot. So I will definitely suggest that at least check that out once. Okay, so that is what comes to a mind. Okay, whenever we talk about reduced dimensionality, that we can maybe use PCA to do it, which is thinking in the good direction. It's very intuitive. Okay, now before moving on with the PCA and discussing what we are doing to the further, maybe we can think about the image a little bit more. Okay, so what was the first reason why we needed to reduce pixels or reduce the dimensionality in the image? What was the number one reason? Can I say that most pixels are black or empty, right? So most pixels are black. This is the first reason why I am trying to reduce the dimensionality or the number of pixels in my image. So I can say this, right? In the MNIST dataset, most of them are black. I don't want the black ones. I only want the ones which are carrying some good information. The black ones are not carrying everything. They are like empty. Okay. What can I say about the second one? The second one is also very understandable. I can say that the neighboring pixels are correlated. Okay, what does this mean? This is also very simple. This is similar to the concept that we discussed in the PCA. So what happens is that whenever we are talking about pixels, so let's say we are taking this pixel and this pixel and then this pixel, so you see how these pixels are neighbors to each other. Now if they're neighbors to each other, there is going to definitely be some sort of correlation between these pixels, which means one feature will be related to the other feature in some way or the other. Okay, so if we have the information about one of this feature, we can also get the information about its neighbor, and we can also get the information about this neighbor. Then due to the information that this feature has, we can get the information about the next neighbor, and so on. So basically this is the concept of correlation, that neighboring features or features which are close to each other, pixels which are close to each other, are definitely going to be related. So no need to keep all of them, which means that again all of these pixels which are in a line, which are neighbors, are not useful to me. Okay, so I'm not going to keep all of them. So this is the second reason why reducing the dimensionality, reducing the pixel here makes much sense. Okay, now there is a third reason. Okay, it is also similar to the first one that we discussed. Okay, we can say that the information, okay, the information or the patterns, okay, the patterns that we want our model to capture are very less compared to 784. Okay, so this is again the same thing. Let me show it to you in the image once more so that it becomes absolutely clear, because this is the concept upon which today's model will be based on, which is why I'm trying to repeat it again and again. Okay, very simple. So we have got 784 different pixels to represent this image. Now as I said, many of them are going to be correlated, many of them are just black pixels. So can I say that the actual information is only being captured right here in this 5? Okay, so the number of features which are actually carrying the information, the number of useful pixels is actually very less. Okay, if I take a different color to make it, uh, maybe I can say with this color. Okay, so maybe I can say that these these ones right here, these pixels are going to be my useful pixels, maybe, right? There can be more, but I'm just trying to give you an example. And rest of all, okay, except the pink dots, rest of all the pixels will be useless ones, because they're either black or they are correlated. So this brings us to understanding the third point clearly. Nothing that information or patterns in the data are very less compared to this 784 feature vector that we have. So this brings us to another reason why we don't want this 784 features or pixels to represent our image. We want some lower value. Okay, now that is the intuition for today's problem. Okay, so this is basically like a recap. We discussed something similar to this in the last problem as well, when we did the PCA. The problem statement there was different, which is why I wanted to do these 3 points again, because the reasons why PCA makes sense or dimensionality reduction makes sense is different for every model. Okay, different for every problem statement that we are trying to implement. Okay, so now after the PCA, the thing is that the PCA might not be the best choice here. Okay, let's discuss it. We'll do everything slowly. Okay, we thought about PCA. Why did we thought about PCA? Because of these three reasons. Now we'll think more in the direction of PCA and its concepts. I'll show it to you. Okay, so now what about the PCA? Now I'm a big fan of the PCA. I think I've said it before as well. Okay, and that is because PCA is mathematically very elegant. Okay, there is no black box in the PCA. You cannot say why is this happening, why is that happening. Everything is right in front of your eyes. Whatever question you have regarding the PCA, if you do the math on your own on a piece of paper using a pen, it will be absolutely clear and you will never forget it. Okay, so the PCA is mathematically a very very beautiful, very elegant solution. Okay, but there are always limitations to every uh, algorithm that we try to implement. It is suited to specific situations. Similar to that, PCA is also tailor made for specific situations, not all. So what are those situations? So this brings me to a very important section that I wanted to show you. So let me quickly get back to the repo once more. This was a very important part to read in the repo itself. So when I open the repo, this is the day 13 repo. Let me quickly go back to the day 12 repo to show you what are some assumptions we make while running the PCA model. So when I open this day 12 repo, you'll see it. Okay. So I have a section in the day 12 repo which says the assumptions made by PCA. Okay. It's just here. Okay, geometric assumptions, this is very important, very important. Okay, open your eyes, ears, whatever, and listen very carefully, very important. Now geometric assumptions, not for the PCA in general, what geometric assumptions are what geometric assumptions are saying is that, you know, they give us an idea as to what model do we have to use. Okay, so before even taking a model and running it, we sort of do the EDA, right, the exploratory data analysis, which is used to basically get us an idea as to how the data distribution is looking, what is the size, the shape, the first 5 rows and all that stuff. Okay, how the spread of the data is looking like, all of that stuff. Now these are nothing but geometric values. Now these geometric values are very important because they allow us to look at the data and make some assumptions. Okay, now what are the assumptions for PCA? Okay, if I see linear data, should I use PCA? Yes, that is the number one most important assumption. Okay, PCA finds linear projections in the data. We discussed this in detail. Okay, which means that if our data manifold, if our data is linear, it is going to be perfectly suited to applying PCA. Okay, but when the data is non-linear, the situation will not be good for PCA. Why? Because PCA has the task of finding linear projections. You cannot find linear projections in non-linear data. Okay, I'll show it to you what that means, but currently just look at it. Just try to understand what we are talking about. What we are saying is that whenever we talk about PCA, we can only apply it when the data is of a specific type, when the data is nothing but linear. When it is non-linear, we cannot apply PCA successfully. It will fail. It will not capture the underlying pattern that we want it to capture. For that, we, you know, apply some different model. So this is important to study the geometric assumptions because this is how we select our model. Okay, now quickly let me get back to day 13 once again. Okay, and then we'll get back to the board and continue what we were doing. Okay, so let me open the board here. Okay, so the PCA is very important. What does the PCA do? PCA is tasked with finding, you know, the maximum variance direction, right? So again, I'll say, if this is seeming puzzling to you, watch the PCA video in detail. I have discussed all of these things there. Okay, if you have watched this will feel like 1 plus 1 is equal to 2. This will feel very intuitive. Okay, so the PCA is tasked with finding the maximum variance direction. Okay, which is fine. Okay, and then what we do is that, I think you remember this, we assume W to be the direction, and then we do the projection of each data point on that direction. So projection of each data point, which was called an xi, on direction W. Okay, which we assumed to be the direction of maximum variance. This is how we solve for PCA, right? And very important, very important, after doing this, in the end what we do is we keep the top k principal components. Okay, k is some number specified by us, top k principal components, which means top k axis, that top k dimensions that represent the data. This is what we are doing in the PCA. Now the thing is, this is all good. PCA, like I said, it is mathematically super duper elegant, it is very beautiful, it is good. But the thing is, the PCA is dependent upon one very important property, that is, linear data. PCA works only when the data that we are talking about is linear. Why is that? Why is that? Okay, I'll show it to you. Why is that? Because this projection that we are making, this is nothing but a linear projection. So I did link an article about linear projection. It was a Medium article by some guy, in the link in description, so you can check it out as well. But if you know about it, it's good. It's a basic linear algebra concept. Okay, so if we have got like a direction W, okay, but we don't know the magnitude, so what we do is we project this xi on this direction W. Basically it means doing this. Okay, this is how we mathematically write the projection. Now this, whenever we talk about this projection, this is nothing but the linear projection. Okay, linear projection. And if you want to understand what it is saying, it is basically saying that W is the direction of maximum variance. Okay, fine. And xi is my individual data point, so I'm trying to multiply them together so that I can project this point into the direction of maximum variance. Okay, because that is what the PCA aim to find. Okay, now the big word here, the key word here, like I keep repeating, is linear. Okay, we are talking about linear projection. This, now this linear changes the entire equation. Why? Because let me tell you what linear data looks like. Okay, so let me draw this xy plane. This is nothing but an xy plane, right? This is y-axis, x-axis. Now what does linear data look like? This is an example of linear data. This is linear data. This is linear data. Basically any data that can be represented using this simple mathematical equation, that is called as linear data. Okay, now what is the constraint? Okay, why are we having non-linear data here? Okay, so the thing is, guys, most of the data in real world, be it text data, speech data, audio, music, images, videos, it is non-linear data. Data in real world, the world that we live in, real life, it never looks like this simple. It never looks like this. It is never like, oh, apply y is equals to mx plus c to get your answer. It is never like this. Okay, so the important thing to understand here is that real world data or in real life data is mostly or usually non-linear. Okay, so in real life data is non-linear. Okay, which means that if you want me to show you non-linear, it can be, there are many examples. Non-linear data, let me draw this xy plane. Non-linear data might look like this. Okay, then might look like this. It can be any shape, yeah, and anything except a line in the xy plane is non-linear data. This is how the real world data is going to look like. You cannot find some simple equation to fit the non-linear data in. That is the constraint here. Okay, and what is the issue with PCA? PCA, the simple thing is, like I said, it assumes that the structure of the data is linear. And so if you try to fit PCA on this problem here, it will be wrong, because it will try to treat it like a linear data problem, and the data that we have in this case, this image data that we are dealing with today, this is not linear at all. Okay, and that is how real world data mostly is like. Okay, so now can we say that we have understood very simple two things? Number one, we understood the very simple thing that what is this? Yeah, that we need to reduce the dimensions. Okay, we need to reconstruct our feature space in some way, so we need to reduce the dimensions. Okay, that is definitely one thing that we understood, because we don't need all 784 pixels, right? And then the second thing, we need to reduce the dimensions, but the data that we are dealing with, okay, the data that we are trying to reduce the dimensions of, that is not linear, that is a non-linear data. Okay, so now this is what our collective problem statement is looking like. It is saying, okay, you decoded everything, you have to reduce the dimensions, but your task is not that simple, because PCA will not cut it. Why? Because PCA is suited to linear data, we are dealing with non-linear data. Okay, that brings us to the model that we are using today, the tool that we are using today. You can call it anything. It's a beautiful tool which is called as an autoencoder. Okay, don't worry about the name is simple. The name basically has nothing to do with it. You will understand everything about it. It's very easy, to be honest. Okay, an autoencoder. Okay, so what is an autoencoder? If you want the definition, You can read it from the repo as well, but like if you want me to define it, an autoencoder is nothing but it's a neural network that is trained in order to reconstruct the feature space that we are dealing with. Okay. Now, very important thing, I mentioned neural network, and we have not covered neural network in this series till now. So if you are hearing about neural networks first, I suggest you can read the link, you can read the article about neural networks that I have linked in the description. If you have some idea about a neural network, it is very good. Okay, it is not exactly being used in here, but autoencoder itself works on the principle. Okay, it itself is a neural network. So nothing to go in deep. You just need to know about basic neural networks, ANNs mostly. Okay. So now that is what an autoencoder is trying to do. So, if I try to write it down, what an autoencoder is doing is that it has got this image data that we are dealing with today. Okay. So it has got 784 pixels for one image, or 784 different dimensions. And what it's saying is that, I will do my magic. Okay, I will do my algorithm that whatever happens in an autoencoder, we will discuss it, but first just understand how it works broadly. So I will apply my magic inside the autoencoder, and what I will do is I will reconstruct this data. Okay, I will reduce the dimensions or reduce the pixels in this data to some lower value. Okay, so I'll reconstruct the data to maybe k pixels. Okay, k pixels. K is some value which is obviously less than this 784, because we don't want a value close or equal to 784, because that means the model has not done anything. Okay, so this is what it is trying to do, the simple thing. Okay, and yeah, so this is the basic stuff that the autoencoder is basically trying to implement. It is trying to reconstruct this input. Okay, so very importantly, now if I write my objective. So every neural network or every model in general has an objective. So just a second. So if you look at the screen, if we are talking about the objective, so we just defined above what the autoencoder actually wants. It wants to reconstruct to k pixels. And why is it wanting that? It is wanting that because basically we are saying not all 784 are important, so reduce it to some low value. And keep in mind that the data we are using is non-linear, so PCA cannot be applied. So we have to apply this new algorithm or this new model, okay, which is called as an autoencoder. Okay, so what is the objective? Basically the objective is to compress the image, right? We are saying compress the image for us, compress the image to some lower dimension, to some lower pixel value. So we are saying compress the image and represent it as accurately as possible. Okay, that is what we want. Okay, so this is basically pretty simple. Okay, so we are compressing the image to some dimensions k, where k is some value less than 784. Fine. Okay, very intuitive till now. But the question is that we might also get incorrect answers, because whenever we talk about PCA, we talk in the terms of variance, right? You can see the day 12 repo once again if you want to, quickly revise things. But let me mention this: whenever we talk about PCA, we talk in the terms of variance. We say, we want to find the direction of maximum variance, then take the projection using the each individual data point, and then basically get the value of maximum variance, which is the eigenvalues and all that. So all the time we're talking about variance, but when you saw this autoencoder definition right here, there is no mention of variance in here. In fact, it is working on that principle only, but there is no real mention of variance in here. Okay, so this is why we need to make the objective very clear, which is why I've written that the image needs to accurate the original one. The image needs to be similar to the equal one as much as it can. Okay, this is because we want to actually capture the underlying patterns in the data and make sure that our model is interpreting it as correctly as possible. Okay, so this is because because of the working of this autoencoder. So the autoencoder, no one tells to the autoencoder what features are mattering. Okay, like in the PCA, how did we decide what features are mattering? Okay, we did it by calculating the variance. We were like, whichever feature has the maximum variance is the most important, because maximum variance means it is capturing the maximum information, which is eventually what we were after. But in the case of autoencoder, we are not calculating the variance. We are not doing any calculation till now. So how will we know that what features are mattering? We will know this by this accuracy. Simple as that. Okay. So let's say I have got my image. Okay, I've got 1, which is represented in the MNIST image. And I'm saying that I don't want 784 pixels, so you reduce 1 to some lesser value so that the representation becomes better, and that I don't need to use as many pixels. So the model says okay, and it constructs me something like this, and it reduces the shape like this. Okay, so this will be like an acceptable answer because it is similar to the original image, and I can see that the size has reduced, which means the number of pixels that we were using before has reduced, so it is a valid result. Okay, so this accuracy, this resemblance to the original image, so this is the original image. Okay, and this is the transformed image, right? So I can say that when the original and the transformed image look similar to each other, we can say that the autoencoder has done its job accurately. Okay, so instead of variance, the accuracy as to how the image has been transformed, or how the image has been reconstructed. Okay, that is what matters here. Okay, that is what tells the autoencoder as to what features are mattering. Okay, very simple till now. So again, this is what we have done till now. If you want to quickly revise it, so we discussed the autoencoder. Now moving on, now comes the main thing to discuss, which is the autoencoder math. Okay, I'm sitting up straight because this is important. The autoencoder math, so very important. As we discussed, autoencoders are primarily used for nonlinear data, right? But the thing is that there are two types of autoencoders. So autoencoders can be linear autoencoders, and they can be non-linear ones as well. Okay, non-linear will be the new thing for us. Okay, now you will say that the linear one is also new. Now it is new, but you will see how it basically relates to PCA. Okay, so first we'll quickly get the linear autoencoder over with, and then I'll move on to the non-linear one. Okay, so the linear autoencoder. Now what will happen in this case? What will happen? My data is still assumed to be linear. Okay, my data is still linear, so I'm like, okay, fine. So let me now quickly show you the architecture of an autoencoder. Okay, so an autoencoder has the first component as an encoder. Okay, and the second component is called as the decoder. Simple. Okay, these are the two primary components in a linear autoencoder. Okay, now we'll just quickly look at what these two are doing. So let's say I have got I've got X, where X is representing the number of dimensions using which my images are represented, or any data is represented. Instead of 784 again and again, I'm choosing this value X. Okay, and I have to reduce it and reconstruct it. First I have to compress all the images to get some lower value, maybe this X cap. Okay, let's call it X cap, the lower value. Okay, that is what I want to do in this case. So what the encoder does is, the encoder tries to learn the input representations, okay, using this equation right here. This is the equation of the encoder. This is basically the task of the encoder in general, is to learn all of the input representations that are happening, to get an idea about the underlying patterns in the data, whatever they may be. Since it's linear data, there isn't going to be much patterns, but whatever the patterns are, the encoder will learn it. Okay, now this X is nothing but the original data. Okay, this Z is the data that we have learned after doing the encoder operation. And what is that operation? We have multiplied it with this WE. Now this W is nothing but the weight matrix. Okay, the weight matrix. Now I will explain about weight matrices later in the video, so you can skip over to that section if you want to. But to understand it, basically weight matrices keep different values of the weights, the learned weights. I've explained them very nicely just about 10-15 minutes later in the video, so you are very welcome to check out that section first and then come back. Okay. And then coming to the decoder, what is the decoder doing? So the task of the decoder is to get the final output, which is this transformed x, the x cap that we wanted. Okay. And it is nothing but the weight matrix of the decoder. It is different from the encoder, multiplied by z, and z is nothing but the representation of data learnt by the encoder. Okay, now very simple mathematical thing we can do. The value of z is the weight matrix of the encoder multiplied by x. So we take this value and we try to input it in this equation. We can do that, right? It's simple math. So how do we then write it? It will be wd multiplied by we multiplied by x. Okay, so this is how the final output of the decoder looks like. Okay, this is basically saying that, you know, this x bar is my transform data, and it is nothing but like this linear projection of the original data. Okay, this is what a linear projection was, if you remember from a little while back. Okay, what I'm saying is that this is my original data and I'm saying it has changed to this. How much has it changed by? What are the changes that have occurred? This is the change that has occurred. Okay, so x is nothing but the original data that we were talking about, the original pixels or the original features, the original dimensions. X cap is the compressed or the reconstructed data, and this is nothing but a linear projection of the original data x. Okay, simple, very simple, right? So basically, this WD into WE combined, since I said that this WD into W is nothing but like a linear projection of the original data, so we try and write it in a simpler manner. Instead of writing WD and WE again and again, we write it as capital P multiplied by X, where P is nothing but this matrix, this total matrix. Okay, the projection matrix. Simple. Okay, simple as that. So now coming to a very important question. Now we have done the task. This is what it learns. Okay, I have explained the weight matrices later, but we are done with our task, right? This is what we wanted. We wanted a linear projection of the original data x, and we have that right now. But how to check it? Okay, what does this mean? How to check it? Like I said, right here in the definition itself, once we do once we use the autoencoder and apply what we wanted to apply and get the results, how will we check that the results that we have achieved are good enough, they're viable enough? We check it by basically calculating whether our transformed image is similar to the original one. Okay, that is what we try to do here. So this x cap is our transformed image or our transformed data, the reconstructed data that we have on our hands, and this x is the original data. So maybe if we subtract them, we can get it right. If we subtract these two, we'll get an idea as to how much the data has changed, and we do not want the data to change that much because we wanted to capture the underlying information. What I'm trying to say is that this x should be near about this value of x bar. Okay, basically the difference between these two should be very less. Why? Because if it is too much, then it means that the task of the autoencoder was incorrect. It is not capturing what we wanted it to capture. Okay, So maybe we can say that if we write it in the terms of a loss function, we can say that this x, which is the original data, and then the px, which is our transformed data. Basically I'm writing this. Okay, when I calculate this, I need this entire loss to be minimized. Okay, I can say this, I can definitely say this, right? This is very intuitive. This is nothing but this is like the mean square error. Like if you look at this very carefully, this is nothing but the mean square error, right? What was the formula of mean square error? The original value, the original feature values subtracted from no the original feature values minus the values of the feature that we calculated, and then we square everything. And here we used to have a summation. I've just written it in short. Okay, if you want to write it, you can like put an xi here for the ith feature, and then you can put a summation 1 upon n here. So this is like the mean square error formula, but for the autoencoder, and we want it to be minimized. Why? Because if these are very different, this xi and this pxi are very different, it will mean that our model has failed to do what we basically wanted it to do, right? So we want this to minimize it. Now how will we minimize this? We will not calculate anything. We'll intuitively try to look and decide how do we minimize this. So what is the minimum value of this? Maybe I can say the minimum value is 0, right? Or close to 0. Of course, the minimum value is 0 or close to 0. It cannot be a negative value, because there is this square right here. So the negative value will be squared and converted to some positive value, which means that the minimum that this L can have, this loss can have, is 0 or close to 0. Okay, now how do we get it to be 0 or maybe close to 0? How do we get that? So looking at this carefully, what is xi? Again, I like to stress upon this. What is xi? It is nothing but a feature of the original data, or a dimension of the original data, a way to represent the original data. And what is this pxi? It is the transform data, or like we wrote before, it is like a linear transform. Okay, like a linear projection of x, or the original data. Okay, so the linear projection of xi. Now this basically means that these two values are same, but only the direction of this is changing a little bit. Okay, so what can that direction be? Now, is this going somewhere? Do you understand where we are going with this? Does this seem even a little bit intuitive? Where do we do these things? No idea. What I'm saying is, where do we ask this question? Where else do you see this question? That we have got the data, and the data has been transformed to some other value, and now we want that value, where that data is maximum. The PCA, nothing. We ask the same question in the PCA. Okay, in the PCA. That is what this is. Okay, that was the big boom, the big surprise. That is what it is. Okay, so if I write it first quickly, listen to me very carefully. The PCA is nothing but the linear autoencoder that we just trained. Okay, so linear autoencoder, when it is trained with the mean square error loss function, like we did here, it basically learns the data representation exactly like we do in the PCA. Okay, I'll again show it to you. So let us quickly go back to the PCA notes. If I can open it, see, these are the notes of the PCA from day 12. I have them right here combined. Okay, so if I open the notes of the PCA and go towards the end to show it to you, what was the result of the PCA? Okay, what was the result that came out? Do you remember? This is what the result of the PCA looked like. Okay, basically we were saying that this is our covariance matrix. W is representing the direction where the variance is maximum. Okay, and when we try to find that direction, we are saying it is along this W itself, but only the magnitude is changing. By how much is the magnitude changing? By this lambda value right here. It is changing by this lambda value. Okay, now isn't this similar or exactly the same to what we have done today? We are saying the xi is our original data. Okay, we don't want all of the features of the original data, so we try to reduce it, we try to compress it. Okay, we have got the compressed one. What is the compressed one? The compressed one is this pxi value. Okay, and we are saying since both of them have xi, only p is changing, and p is representing nothing but the projection matrix, which means the direction matrix. So in what direction can I think? Where is that direction such that this loss function right here is minimized? Where is that direction? It is going to be the direction where there is the maximum value of the eigenvalues that we calculate. Okay, so the maximum basically the maximum value of eigenvalues of this p matrix is going to be the direction where this will be closest to x of I. Okay, another way to understand this is very simple. Maybe you can go back to the PCA again and really try to derive the results. You will understand. Okay, very important to understand this. This is why we did the linear autoencoder. I could have skipped it entirely, but this was very important because the linear and autoencoder combined, when it is trained with the mean square error loss function, it basically learns data just like the PCA does. So it is like PCA itself. That is the result that I wanted to basically get at. Okay, this is how it works like. Okay, and this mean square error, now it is actually mean square error, but in the case of autoencoder there is a different term for this loss. It is called as reconstruction error. Okay, it is like the formal word for this, reconstruction error. Okay, so if you have any confusion or doubt about that part, you can definitely watch this part again to be a bit more clear about it. Also, as usual, I have left an article in the description that you can read about the same thing. Okay, it also explains in the similar way very intuitively as to how a linear autoencoder when thought about is just learns like the PCA. Okay, so this is nothing but the reconstruction error. Okay, so again let me quickly go back once again to show this to you. Okay, so let me quickly go back once again to the PCA. So this is what we were doing in the PCA. This is we got the variance value as lambda, and lambda, I told you, it is nothing but a term in linear algebra called as the eigenvalue. The name doesn't matter. What matters is what does lambda represent. It is representing the direction, or it is representing the magnitude of maximum variance. Okay, basically the direction where the maximum data will be captured. Okay, and w, which is representing the direction, means the eigenvector. Now when I am trying to calculate my reconstruction loss right here, I'm saying how to minimize this, which means that in which direction should p go, in which direction should this p matrix be, so that these two values are close to each other. It will be in the direction where the eigenvectors have maximum eigenvalues. Okay, so it's nothing but the PCA that is being learned here. Okay, simple as that. So now we are through with the linear autoencoder, which basically brings us to our main problem for the day, which is the non-linear autoencoder. Okay, so again I'll say, any doubt about this as to how the PCA is basically the linear autoencoder, you can read about it very clearly in the article. The article is a very well written, which is why I've used it in the description. Okay, reading will basically clear all of your doubts. If you still have doubts, you can take a pen and paper, try to solve everything out on your own, and it will definitely be clear. Okay, now let's move. So now we get to the non-linear autoencoder. Okay, that is the main deal for today, because that is what we are using in today's model. It is the strong autoencoder version. Okay, so I'll discuss it quickly. So let me first write one last thing for this linear autoencoder. So we can say that top k eigen vectors of feature space get us minimum reconstruction error. Okay, so this is nothing but what we just discussed right now. So what I'm saying is that the feature space is now being represented by this P, which is the projection matrix multiplied by the original data. So the top k eigenvectors of this matrix P can give us the maximum value of pxi, the value which is closest to xi, so that this entire function here, this entire loss function, okay, this entire reconstruction error becomes minimized. Okay, that is what you can say we are trying to do. Okay, now on our way to nonlinear PCA, nonlinear autoencoder. Okay, so non-linear autoencoder. Okay. So now for the first thing, before even writing something, I would like to discuss what is the primary difference between linear autoencoder and non-linear. So linear, we can say that it was still dealing with the linear manifold, which means linear data. It was assuming that the data is linear. Non-linear will, of course, very intuitively, it will assume the data to be non-linear. But there is another difference. See, non-linear autoencoders introduce the concept of activation functions. Okay, so again I'll say activation functions are a concept related to neural networks. So if you have not studied or not even heard the word activation function before, I will definitely say first check out the link in the description regarding neural networks. Okay, it explains activation functions as well. That way you will have a much better idea as to what we are doing here. If you are comfortable with activation functions, let's just move forward. Okay, so if I try to write it, what is like the task, the primary task of activation functions? So you see, activation functions, they want nothing special, but they want to capture the non-linear patterns in the data. It can be any activation function. The basic task is it wants to capture underlying patterns in the data, especially non-linear patterns in the data which are not easily seen. Okay, so underlying non-linear data patterns. Okay, that is what the activation function tries to go after or tries to capture. Okay, simple. Now what will happen when we try to train the non-linear autoencoder? So the non-linear autoencoder has a similar kind of an architecture. Okay, like we had in the linear autoencoder, it has got an encoder which tries to learn the representation of the input, and then the decoder which tries to produce a final output. So for the encoder we can write that let's say we have got h1 as the learned representation by the encoder. Okay, now I put this sigma here. Okay, now this sigma, or yeah, this is called as a sigma. This is the Greek symbol sigma. This is representing an activation function. Okay, now this symbol sigma symbol right here, it is used to represent the sigmoid activation function. Okay, but in this case we are not representing the sigmoid specifically. We are using this symbol to represent the activation function in general. Okay, it is not actually the sigmoid, it is something different. We'll talk about it, but let's just use this. Okay, so whenever you see this symbol, it basically stands for us using the activation function. Okay, so we apply the activation function, and inside we get the weight matrix for the encoder multiplied by the raw data X or the original data X. Okay, so this is the learned representation in the hidden layer, in the inside layer of the encoder. Now what is the output? Now the output is represented by Z, and it is nothing but something like again an activation function, okay, multiplied by some different weight matrix W2, okay, multiplied by what we get in H1. Okay, so there are two steps in the encoder here, and it's very easy to understand why there are two steps. See, as our data becomes non-linear, the patterns underlying in it, the patterns that are present in the data become more difficult to capture. We need to find new ways, we need to find more complex ways in order to capture that, which is why we introduce the concepts of layers. So earlier we can say that the autoencoder had only one layer. Here it has two layers. So this first layer, H1, it tries to capture the underlying data patterns it has, the hidden patterns it has using the activation function. And then this second layer is basically to return the output in the final form. Okay, and of course, by doing a basic mathematical calculation, we can input the value of H1 in this equation, and this way we can basically get our final output. So we can say that the encoder eventually gives out this value, activation function W2, okay, activation function again, and inside this we get W1 of X. Okay, and here you can like put a dot or a bracket, whatever you want. So this is the final output we get from the encoder. Okay, simple. Now before moving forward, I'd like to really discuss what this activation function here really is. Okay, so this activation function, which is specially used in all of the hidden layers in the encoder and the decoder, is nothing but the ReLU activation function. Again, it will be confusing if you have not read or heard about the ReLU activation function before. If you have some prior knowledge on it, good, you can move forward. If you don't, first get some idea about it, otherwise you will end up confused. Okay, so the ReLU activation function, what it says is that whenever we apply this ReLU on some value X, it will basically get rid of any negative values. So the output will be like this. Okay, this is how the ReLU works like. This is how it looks like. It's very simple. So if I put some negative value instead of this X, let's say I put -1. Now the output will still be either 0 or some positive value, because it is saying take the maximum of 0 and this X, and this X here is nothing but -1. So what is the maximum of 0 and -1? It is 0. Okay. Similarly, you can take any value of X. The minimum value that ReLU can have is 0. Okay. And the maximum value it can have is X. Okay. Because, if I give X a positive value, let's say I say maybe this is the value of X, then what will be the output of ReLU? It will be nothing but the maximum value between 0 and 5100, which is nothing but 5100. Okay, so now why are we using the ReLU in the hidden layers, in the inside layers of the autoencoder? The reason is that the ReLU is first of all very good at handling the problem of vanishing gradients. Okay, ReLU is extremely fast, it is piecewise linear. Okay, and it basically gives out all values which are non-negative. It's the perfect thing to use inside a hidden layer. Okay, this is why we use the ReLU. Okay, so with that, we get towards the decoder part, because we have already discussed the encoder, and now we have got this idea as to what this sigma value is representing. It is basically representing the ReLU activation function that we have on our hands here. Okay, now the second part. What about the decoder? So as I told you, the decoder is basically responsible to give us the final output, to reconstruct the image and give it back. So let's say that H2 is like the maybe like the hidden layer in the decoder. So it will look like activation function, okay, and inside we have some new weight matrix W3 and Z, and Z is nothing but our output from this encoder that we have, okay. And after this hidden layer, the decoder will give its final output. So the final output will be nothing but reconstructed X, which we eventually wanted as our problem. And again, we get the activation, some new weight matrix W4 multiplied by H2, which is basically the information in the hidden layer of the decoder. So this is what the final output looks like. Now, of course, we can, open it up mathematically. You can do it yourself, or maybe I'll do it quickly. It's very easy. So this H2 value can be put here. Okay. That way we will get this sigma, then W4 multiplied by activation function sigma again, W3Z. Okay. Now this is not done. I know this already looks pretty big. It doesn't matter how big it looks because we understand everything about it. But if we go back and we try to look at what we got from here. So the Z value that we got from the encoder can also be input back in here, right? So when we do that, we get the final feature, okay, reconstructed. So activation function, then the weight matrix multiplied by the activation function again, containing the weight matrix W3, activation function once again, and inside that we can copy the value that we calculated as Z in the encoder output. Okay, so this is how it eventually looks like. This is how the final output looks like if we open it up mathematically end to end. Okay, no need to memorize any of this, by the way. Okay, this math is very easily available anywhere online if you find it. I was just trying to do everything from the first principles from scratch so that everything is very clear and there are absolutely no doubts, because many a times you see this result written and then you ask yourself that why didn't I study this, or where do these values come from. So this is how simply you can derive it. You can derive it yourself as well. You just need to remember the equations, or you can look up the equations and derive them. Okay, the main thing is to understand the key intuition behind the non-linear autoencoder. Okay, now one very important thing that I forgot to state. Okay, so when we do this last step in the decoder to find the output, this activation function is not the ReLU. Okay, so this one is the ReLU, the same ReLU that we just discussed above. Okay, this ReLU, and the ones in the encoder, this one and this one, both of them are ReLU, but just this last activation function that we get here, this is not the ReLU, but this is actually the sigmoid activation. Okay, why do we use the sigmoid? Okay, so first let me quickly show it to you. How does the sigmoid look like? The sigmoid is used in the logistic regression as well. We covered it on, I think, day 1 or day 2 of this series itself. Okay, so this is the symbol of the sigmoid. Okay, looks like, or maybe you can write Z here, Z. Okay, 1 upon 1 plus e to the power minus Z, and this basically squashes value between 0 and 1. Basically, whenever we apply this function on some value Z, we always get a value either between greater than 0 and less than 1 between these features. Okay, so now let me quickly open the repo just once in order to show you the significance of these activation functions. So let me, yeah, so you can read about the activation functions here as well. So sigmoid is only used at the output because we need to normalize the features. Okay, it squashes any values between 0 and 1, and basically this is why it is used in the output, so that we can basically match the range of our target variable. Okay, and why is the ReLU used in the hidden? Because it introduces non-linearity, then all of the advantages that ReLU has. Okay, it gets rid of any negative values. It generalizes well. It is fast to train, piecewise linear, avoids the vanishing gradient problem, and all of these things. Okay, very good. Simple. So let's quickly get back to the board and continue. So this is why the sigmoid is used in the output. Okay. Now we are done with most of the math. Okay, good thing there is no more math to be discussed now, but some very important concepts. So quickly, the juice that I have been wanting to get to very quickly. So do you see these weight matrices? Do you see these weight matrices? Of course you do. You see this W1, right? I told you this is a weight matrix. See this W2, it is also a weight matrix. W3 is also a weight matrix. W4 is also a weight matrix. So what do these weight matrices mean? What are their values? Where did they come from? Why are we even using them? So this brings me to a very important concept that was like a black box for me for a very long time. Like you know till I had gotten pretty far in all of the concepts of AI, and I still was not clear about how these weight matrices really work like. Okay, so weight matrices are basically used to approximate these complicated non-linear functions. Okay, how do they work like? So the thing is, let's say that I've got the first layer of the encoder, this. Okay, so activation function, and inside I have w1 into x. So let me quickly write it. Okay, let's say I've got w1 multiplied by x. Okay, now since I said this is a matrix, so this is not a single value, so it can look something like this, right? It will be like this matrix, this 1D matrix. Now what are the values inside this matrix? The answer is very simple. The values are initialized randomly. Okay, hear me out very carefully. So the values inside this matrix are given randomly initially. Okay, these are random values assigned in it. See, random values like this. Okay, now how does this work like? See, whenever we try to run a neural network and we talk about weights, so values are initialized randomly. Okay, this is because these weight matrices are not memorized weight matrices, they are learned weight matrices. Their values are updated constantly. How? So when I initialize these values randomly, then what will happen now? This w1, each value of w1 will be multiplied by this x. Okay, this x also is a matrix, so it will look like x1, x2, x3. Okay, all the way to xn. Okay, and then each of these values are multiplied. This is multiplied with this, this is multiplied with this is multiplied with this, and so on. And another bias term is also added. Okay, it was not relevant to the situation, so I didn't mention it, but a bias is added. Okay, and we basically get these multiplications, all of them, all of these multiplications. Now when these multiplications happen and we get the decoder output, so this way we do this for all of them. Okay, this is for w1, we do it for w1, w2, w3, w4, all four weight matrices, all four equations that we discussed right here. Okay, two for the encoder and then two for the decoder, and then finally we get this output right here that we wanted to get. Now after we have this output, what do we do? What did we do? We calculated the loss function. Now what is the loss function in this case? The reconstruction error, right? So then we calculate the reconstruction error, right? Okay, simple. Now the thing is, when we calculate this reconstruction error, it will have some horrible value in the beginning. In the first step, it will have some horrible value. Why? Because these values of the weight matrix are initialized randomly. These are random values now. These are not trained values. I just gave random values to start the model. So now, you know, the model will try to update, okay, the model will try to update weight values. Okay, how does it do that? By calculating the gradient. Okay, so the gradient is basically the slope of the loss. It basically gives us the direction where the maximum loss is occurring, so that we can go to the opposite of it and basically converge our model. Okay, so simple. Values of the weights are initialized randomly. Then this matrix multiplication happens, this w1 into x that we did, and some bias value, random bias value is added. After that, we do this for all four weight matrices, w1, w2, w3, w4. Okay, we then calculate the reconstruction error, which we discussed. What's the formula? After that, we'll see that the reconstruction error is having some huge value. We don't want that. We want the error to be minimized. So to minimize it, we will try to update the value of weights. So, in the first iteration, the weight values will be updated. Then the model will be trained again. Then again the reconstruction error will be calculated. It will still be some very large value. Now the model will say the weights are still off. You need to update them again. And this process of updation, this process of updating the weight matrix or the weight values will keep repeating until we get to model convergence. Okay, basically convergence here means that our reconstruction error reaches some sort of minima, some sort of minimum value. Okay, so it will keep repeating till then. Okay, so this is how weight based gradient training really works. This is the intuition behind the weight matrices that we initialized, and they're all different because they are being used in different scenarios. They're all initialized separately, okay, and randomly. We don't know what are the values in the beginning. We can never know. Okay, so this is how this happens. Okay, simple. Now we are slowly getting towards the last few concepts that we have to discuss. Most of the stuff now is done, but one very important concept still remains, which is the juice in this non-linear autoencoder topic. Okay, so now quickly look at this. What was my problem initial? If I go back to the first page, my first problem, it was simple. I was saying, this is my data X, okay, and it is being represented by D dimensions in the real feature space. Okay, so D dimensions are being used to represent X, but I don't want D because D is too many. So I want some value different than it. So you should transform my data to Z or X bar, whatever we can take it, and Z should have only K dimensions. Okay. Now the thing is, when I try to pass this problem, when I try to say that my original data X is being represented by D, I needed to reduce it to some other value. Now the thing is, when we train this model without giving any constraint, without giving any value, it will just say Z is equals to X. Okay, do you understand? The model is basically saying that okay, you want me to reduce the dimensions, you want me to reduce the data set, but still keep most of the important information. So what I'll do is I'll basically reduce myself and I'll make myself equal to the original data. Now does this make sense? Does this make sense? See, I am saying I want to reduce X to some value different than X. Okay, and the model is saying okay, I have reduced myself, but I have become exactly equal to X. So did the model actually learn anything in this case? No, no. There was no learning. There was no learning when the model is basically saying I'm same to the original data. Okay. So there is a very important constraint that we need to apply. There is a very important condition that we need to apply here in order for this model to make sense. So we need to apply this constraint. K is less than D. Okay, this is very simple, but it's often a very confusing topic because people don't try to understand it in terms of visualization. Okay, so what I'm saying is I'm saying transform my data from X to Z, and the model is saying okay, I will just make it equal. Z is equals to X, and this is also a transformation because both of the features are the same. So I can maybe say that you know, z is nothing but 1 into x. And this is how the model is trying to, you know, fool you by trivial learning. It is saying, yes, I have changed x, I have multiplied it by 1, and I have changed x, but it is actually the same thing. The model hasn't really learned anything. So to make it learn something, we need to assign that this k value, okay, the new dimensions that we want should be some value less than the original one. Okay, that is how the model is sort of forced to understand and learn the underlying patterns. Okay, so again, instead of x and z, if I write it in a much better example, I'm saying this is my image having 784 features. Okay, no, I don't want 784. I want you to represent my image x using some different vector, using some different you know, data space. So you will represent it using z. Okay, z. And you know, you haven't given any constraints, so the model will say, okay, I'm using z, and z is nothing but z is exactly equal to x. So here, this is called as the case of trivial learning. Basically, you know, the model has fooled you because you did not give it some constraint. So you need to specify that, you know, when I say that x has 784 features, I want z to have k features where k is some value less than 784. Okay, what happens is that you can imagine it like this. Let's say I have this cave. Okay, cave, like a literal cave that we find in various places. I'm saying that, you know, this space is representing 784. Okay, and you can take 784 features inside it, but this space is nothing but something like 32. Okay, so you have taken 784 features inside it, but this distance right here is limited. You can only take 32 features inside it. So this way you will definitely take only the most important features. Okay, you can understand this in some other way. Okay, don't look at the screen, look here very carefully, look here. Okay, so you are on the Titanic or you are on some ship. Okay, the ship is going to sink, there are no lifeboats, you will sink, you will get in the water in about 5 minutes or whatever time. Okay, now you have got many things lying on the ship, you have got 10,000 different objects lying on the ship. You have maybe a tube, then maybe you have rope, maybe you have dry food, water, whatever, you have all these things lying. Now when I say that you are definitely going to get into the water due to this shipping wreck in about 5 minutes, will you gather everything? Will you take all your clothes or your luggage, or will you take your phone or your laptop? No, because these things won't make any sense. You will take only and only the most important things. Okay, so let's say that there were, you know, 784 different things lying on the ship. You will not take 784, you will not even take 700. You will take the top 30, 20 type of things. Okay, why? Because those are the things most important for survival. Okay, so that is like a good analogy to understand from. This is similar here. Okay, so this transformed feature space that we are dealing with, it needs to have dimensions far less than d, because that is what forces it to understand the underlying structure. Okay, so this very important, this k right here that we discussed is called as, it is formally called as the latent dimension constraint. Okay, the latent dimension basically means the dimension that lies in the middle. This is the dimension that we achieve between the encoder and the decoder. Okay, so k is called as the latent dimension constraint. Okay, very important. You do need to, you know, sort of memorize this because this is asked in many places. Okay, so now let me give you like a quick map as to how it all works. So you know what you will have on your hands is you will have an image. Okay, now the image has nothing but 784 pixels. Okay, we have mentioned 784 so many times in this video. Then nothing, we pass on this image to an encoder. Okay, The encoder will learn the representations from the input. Now from the encoder we go on to the latent space, okay, where we are basically saying that, you know, reduce 784 to some value k, where k is, you know, far less than 784. K is not something like 700 or 600, because that is still a very high value. We need a very low value. Okay, why do we need a very low value? Because that is how the model will be forced to learn some underlying structure. Otherwise it will say, okay, 784 features, I'll use 700. 700 is still too much. Okay, the most important stuff won't be kept. There will still be a lot of noise. There will still be a lot of useless stuff. I don't want that. No one wants that. Okay, then from the latent space we basically go to, you know, the decoder. Okay, and the decoder is doing the task of reconstruction. reconstruction okay, so reconstruction. Okay, and then basically the final output image is being produced back again. Okay, so, you know, what about this value of k? Very quickly, now we took an example of 32. Maybe 32 can be a value. Can something else be a value? Yes, of course it can. There can be a value 64 as well. There can be a value 28 as well. There can be some other, you know, 23, 17, these types of value as well. The point is, this k here is not some intuitive value. It is rather a hyperparameter that we need to select very carefully, because if we take a very high value, like I said, it will not make sense, because that way the model will not learn anything. And if we take too low of a value, then it will be very aggressive in learning the features. We don't want any of those two cases. We want the perfect value, the middle value, which is why we go for usually something in this range, especially for the size of data set that we are dealing with today, the MNIST data set. Okay, so now maybe I can write it in mathematical terms. So let's say I've got 784 as my you know, initial input image. 784 is reduced first to 256 while learning the representation in the encoder. 256 is then reduced to maybe 64. Okay, 64 is then reduced to 32. Okay, now very important, this, just a second, this 784 was the input. Okay, and these three reductions till now are happening using the encoder, because the encoder is learning the underlying patterns first of all. Okay, then we get to 32. What is 32 here? 32 is nothing but the k that we decided. So 32 in this case we can say it is the latent dimension constraint. So latent dimension constraint, this is 32 that we have selected here. Okay, now after 32 the decoder scales the image back to its original one, which is nothing but 784. Okay, so 256 and maybe then 784 again. Okay, and this image right here, it is called as the reconstructed image. Okay, now last concept remaining. Wait, bear with me, stay with me. Last concept remaining, very confusing thing. At least it confused me in the beginning, maybe it didn't confuse you, you know. So very natural question comes in. So the question is like, you know, we had this input of 784. Okay, we wanted to reduce it to capture the underlying pattern, so we took this value k and we reduced it. Now why are we increasing it again? See, our task was to reduce the 784 to some other value so that it learns the underlying features. So we reduced it from 784 to 32. Now why are we increasing it from 32 to 784 again? Isn't that beating the purpose? Right? It looks like that now, because once we have reduced it right here, our steps should have been over. Why are we doing these steps? Okay, so these steps are actually very important. Okay, because they will be used for the comparison. Okay, they will be, I repeat again, they will be used for the comparison. So now let me quickly tell you how it works like. So there's an example that an analogy that I've used here. So very important, don't think yourself, don't think about this concept yourself. You will definitely get confused. Just listen to me, you will understand it. Okay, let's say there is a book. There is a book. Okay, any book. It has 784 pages. Okay, let's say it is some machine learning book. Okay, and your friend gave you this book that, you know, hello, I have this book having 784 pages, and no one wants to read such a thick book, no one wants to read these many pages. So your friend says, can you make me a summary of the book using only 32 pages? Okay, so your friend is saying, I don't want to read this massive book, so I want you to make me the best summary there exists for this book, covering only and only the important stuff. So this 784 pages, you have the task of transforming it to 32. Okay, so you studied, you wrote this summary, and you know, you made this summary of 32 pages for your friend. You were like that, you know, yeah, the 784 pages were useless, most of it was junk. I took the important stuff and I wrote it in 32 pages for you, which you can use to study. It's fine. Okay, now your friend says, okay, thank you so much, but you know, he asks a question. He's like, how do I know you have done a good job? Okay, I say it once again. Your friend asked you to convert this 784 page book to a 32 page book for his summary. You handed him the summary. Then your friend was like, okay, thank you so much. But how do I know that this book is good enough? How do I know that your 32 pages are capturing everything? Maybe you made a bad summary. I don't know. How can I compare it? Okay. Now I cannot go around comparing these two. Can I compare these two? No, I cannot, because it will be like, this is such a large book. This has 784 pages. And this book, on the other hand, is very small. So I cannot compare them. How can I compare one thing which is so big and so small? It won't make any sense now. So a friend will say, I am not able to compare the work that you have done, so it is useless. This is why. This is why. Now what you'll do is, you'll use your own 32 pages, the summary that you made. Okay, this summary contains the most important information in the book, the best information in the book. And based on that, you will make another book of exactly 784 pages. Okay, you will make another book having exactly 784 pages. Okay, now why are you doing this? Do you understand what we have done here? This book has the original book, this has 784 pages, and the book that you made, which is the reconstructed book. Okay, the reconstructed book, it also has 784 pages. But these are not the same pages. These are different pages. Why? Because this reconstructed book is based on your summary of the 32 pages. Okay, very important. I'll repeat it quickly once again. So your friend gave you a 784 page book, and he asked you that, can you make me a very good summary out of that? You was like, you were like, sure. So you made this 32 page summary. But then what you said was that, your friend said, okay, this 32 page summary is good, but how do I compare it? How do I know that yours is good enough to the original book? How can I compare your summary with the original book? And I cannot go about comparing them randomly, because your summary is very small and the original book is very large. So what you say is, okay, I will use my summary to make another book of 784 pages. Okay, it will be different from your original book, but now since 784 and 784 are equal, you can compare them to decide which is better. Okay, very very important. That is exactly what we are doing here. Okay, so once we converted this 784 pixel image to 32 pixel, most of our task is done. Our feature compression task is over. But now we cannot compare. Now we needed to compare to check whether our image is good enough, whether our image is good enough as the original. So this right here, at this step right here, this is nothing but a 32 pixel image. Okay, and in the original image we have like a 784 pixel image. Now can we compare them? No, we cannot. They are completely different. A 784 pixel image is very very superior. compared to something like a 32 pixel image. So how do we compare our results? How do we say that, yeah, we got a good output? What do? We take this 32 pixel image, because these 32 pixels contain the most important values. Okay, it contains the heaviest of the concepts, the best underlying patterns in the pixels, and we, using these 32 pixels itself, we convert it back to the 784. Okay, so the number of pixels is now the same. These are not same pixels, just the number of pixels is same. This is the reconstructed image, and now we can say, okay, the reconstructed image is 784 and the original image also has 784. So now you can compare the original image with the one that I reconstructed to decide which is better, to decide whether our non-linear autoencoder did a good task at reconstructing the data. Okay, so the encoder here is basically doing the task of compression. Okay, compression, data compression, and the decoder is doing the task of reconstruction. Reconstruction. Okay, so in a way you can say that the reconstruction is only used to, you know, basically check our results, to basically convey whether our output is good enough or not. Later in the end we discard the decoder. So this is the decoder step. In the end we discard the decoder because we don't need the decoder later. We only want the representation till here. But as part of the entire model, the decoder and the reconstruction step is very important, because without them we won't be able to compare our results. Okay, that is the intuition here. Okay, so we basically use the reconstruction to produce a target that we can compare with our results. Okay, very good. So now this is mostly done. This was, I think, it for all the concepts involved for this autoencoder model today. If I go back to the repo, you can read all of this, by the way. Okay, I'll quickly go to the code. So this is all about the concept C. This is the decoder and encoder explained. This is, we have discussed this entirely. If you have some doubts, you are very welcome to read it. Okay, information about the hidden layers. This is the same math that we did using our hands. So in this case, what they have done is they have used another hidden layer. So do you remember we used only one hidden layer? We used only H1. In this case, they have used H1 and H2 both. So I wanted to make the math a little more formal for the repo, which is why I took two hidden layers. So in real world data, since there are lots of patterns to be captured, the hidden layers which are capturing the patterns are also increased. Okay, and of course in the decoder, like I said, in the end the sigmoid activation function is used, which is why you can see the sigma here. And in rest of all the steps we have relu, relu and relu, relu. Okay, then the loss function, which is nothing but the reconstruction loss, which is like the mean square error. In this case we calculate it. Okay, now the training parameters. So very important, I think I have not mentioned till now what an epoch is. So an epoch is like an iteration, but it is like one complete forward pass and one complete backward pass combined. Okay, so what does this mean? So like, you know, we start in the beginning where we calculate all of these weight matrices W1, W2, W3, W4, W5, W6. We have got 6 in this case. We calculate all of them. Then we calculate this product. Then we add it to the bias. Then apply the activation function. Then get this final output. Then we construct, then we, you know, calculate this reconstruction loss. Then based on what that loss value is, we do the gradient, we calculate the gradient, and then we update the values. Okay, so this step where, you know, we are doing all of these calculations, this is basically called as the forward pass. And the weight updation that was happening, it happens in the backward pass. So one forward pass plus one backward pass combined equals one epoch. Okay, so one complete iteration. So you can read it. This was the batch size that we implemented. So there are different values of batch size you can take. You can take 32, 64, 128, 256, depending on what data we are training with. Okay, So we took 256 because it came out to be the best value to be taken. Okay. The optimizer used in this case is Adam. So I have another repo and another video on optimizers from scratch. So if you want to understand how this Adam optimizer is working, you can understand it from there. In short, what this optimizer is doing is that it is basically helping us with the weight updation process in the backward pass. Okay. This is how the back propagation will look like. I did not discuss the math. I have put it in the repo because it is too complicated. You can maybe skip it as well. Okay, but you are very welcome to check it out. This is the bottleneck or the latent dimension constraint that we discussed, that we need to assign this k for a value far less than d. So we have assigned 32, very less than 784, because this is how the autoencoder will learn some underlying data. Okay, this was it. Okay, so now let's first check out the code, which is very important. So first, this is the first time in this entire series that we are using TensorFlow. So till now we were relying entirely on sklearn for all our models, but since this is a neural network, neural networks are usually trained using the TensorFlow or the PyTorch library. TensorFlow is much more intuitive for these simple neural networks, which is why we have implemented this. So this is how you import the TensorFlow. Then all the classic imports that we do, NumPy, and after that we have got Matplotlib and Seaborn for the visualization. Okay, scaling here is important. We have imported the PCA. Okay, so why have we imported the PCA here? Because as a part of the experiment in this repo, we compared the results of PCA and the autoencoder to see which is better. And of course the autoencoder will be better in this case, and the reason is very simple. See, that is because the PCA is more suited to linear data, and the data that we have today is not that linear. Okay, the MNIST is an inbuilt data set. This is how you can basically import it from Keras. Okay, Keras is it is a wrapper for the TensorFlow. Okay, the EDA. So this is a sample digit that we plotted. I showed it to you in the repo itself. The EDA basically consists of us printing this image to get an idea how it looks like. Okay, this is a 28 by 28 image. Let's quickly get back to the code. Now the pre-processing. These four are crucial steps, important steps, very important steps. Okay, so let's quickly discuss why these steps are very important. Okay, so first of all, what is happening here? So whenever we talk about the MNIST data, so the data images that we have in there. Okay, so each of the image is a 28 by 28 image. Okay, let me quickly open the board so that it becomes a lot more clearer. So all of the data is nothing but a 28 by 28 image, right? And it basically means 784 pixels. That is what we have discussed in the entire video. Okay, now each of this pixel has a value. Okay, each of this pixel is represented as a value. It is represented as UINT8. Okay, this means nothing but unsigned 8-bit integer. Okay, unsigned 8-bit integer. This basically means values like 0, 1, 2, all the way up to 255. This is how an unsigned 8-bit integer looks like. Okay. Now the thing is that neural networks or machine learning models in general, they do not like integer values, because integer values are, they're not very smooth to work with. Whenever we try to calculate the gradients, we try to calculate the matrix multiplications and everything, the integers are not smooth to work with. What is smooth to work with are floating point values which have a decimal. Okay, floating point data or floating point values are much more natural and much more easier to work with. Okay, so what we do is we convert this unsigned 8-bit integer values, which is representing each of our pixel, to floating point values of 32-bit. Okay, 32-bit. Now, very important question. So, first of all, a quick example. So, if the integer is looking like this, the floating point value will look like this, 1.0. There isn't a much big of a difference, but it's just that these floating point values are very natural to work with in the neural network. Okay. Now the question is, why 32-bit? Why not 64? Because floating point values exist with 64 bits as well. The reason is because these 32-bit floating point values, they are the norm for training any neural network on a GPU. So if you're using any GPU to train your neural network, the 32-bit integer is the most intuitive. It is basically the standardized floating point value which is used to train on the GPU. And also this float 32, this is how we write the floating point value of 32 bits. So this float 32, it takes or consumes only 4 bytes of memory. Okay, so it is very memory efficient. If we use 64, it would take double, it would take 8 bytes of memory, so there is no need to use that. So this float 32 representation makes it GPU efficient, it makes it memory efficient, and it makes it suitable for uh, neural networks. Okay, which is why in the code itself, if we see, as the part of the first step in the pre-processing, we have done this. We have converted our original unsigned 8-bit pixels to floating point 32-bit floating point numbers. This is the syntax on how to do this dot as type. Okay, then of course we have to normalize our feature values. Different values of this training and testing data set will come out, and we want them to be in a comparable scale. So for that, we basically normalize it by dividing it by 255. Okay, now the second important step, the rest of the code is very easy to understand. These were the most important things. What is this? Why are we reshaping the training data? Okay, so let me quickly show this to you once again. Okay, so when I talk about the training data, if you go and print the training data, the X train, the training data, so it will look something like this. This is how the training data will look like. What does this mean? It is saying that there are 60,000 images, and each image has 28 pixels representing the row, and 28 pixels representing the column, right? That is what is given to us. But whenever we train our model, so let's say we quickly go back to the code once again. So whenever I'm trying to train my model, and I'm trying to apply my stuff, see what is happening here in this line of code, line 40. So in the input layer, I try to give the shape as input dimension comma something. Okay, and that input dimension I've declared it as 784. So basically in this case, I am expecting, the model is expecting a 784 pixel value, a 784 dimension value. But when we look at the raw value of X train, it is not 784, it is 60,000, then 28, then 28. Now the model is not expecting a 28 by 28 matrix. It is expecting a single matrix having this value 784. Okay, so to do that we basically reshape our data. Okay, and when we reshape our data, we write it like this: -1 comma 784. Okay, now very important, where did this -1 come from? It is a very natural question, because the 784 is fine. We can say that we wanted to write it down as a single 784 features, so we wrote this because this is what the model is expecting. Where did this -1 come from? So this -1 is basically saying that it is saying to the model that you can calculate the value of this dimension or this feature yourself. So how will it do it? It will basically say if it wants to calculate the number of images, so what it will do is it has got 28 into 28, okay, which is nothing but the feature matrix that we have. It will multiply that by 60,000, okay, and it will get some value, and then it will divide it with 784 once again, okay. So this and this will get cancelled, and basically the end result that goes inside the model will be this, okay, and this is what eventually the model is trained on. Okay, so whenever we write dot reshape and we mention -1, it basically means we are saying it to the model that this feature value you can calculate it yourself, and to calculate it yourself it does this process. These are basically the training images. This is our features represented as a whole rather than as a matrix. Rather than as a 28 by 28 matrix, we are trying to represent it as a single value. That is what this is doing here. Okay, so this is why we try and apply this dot reshape here for the training and testing data right here. Okay, these two are the most important things in the model. Rest is very easy. So now we just implement the autoencoder architecture. The latent dimension constraint, the k value, we took it as 32. The input is nothing but 784. You can declare it before, you can declare it inside here as well. I just want to keep the code clean, which is why I've declared it here. Okay, now the autoencoder, it has two hidden layers. Okay, so I get this dense. Now this is the basic syntax. You can maybe practice it regularly to sort of get it inside your mind. This dense basically creates like a small like a small ANN, like a small neural network. Okay, it has the batch size is 256 initially. Activation function is relu. Okay, simple. And then there's the second layer. The batch size now is 64. So you remember how our model was decreasing. It was from 784, 256, 64, 32, and then increasing again. Let me show it to you how we did it. This is how we were sort of doing it, right? See, this is what we were doing. 784 to 256 to 64. That is exactly what's happening in the code. See, 784, the input. Oh, sorry, the input right here. And then we go on to 256, 64. And then eventually we go on to the latent dimension, which is nothing but 34. Okay, and after that we go on to the decoder. So for the decoder now we are starting with the image reconstruction process. So the number will increase once again, the dimensions. So it increases to 64, 256, and then finally 784 once again. Okay, and in the output layer of the decoder, the activation used is sigmoid. Okay, everywhere else it's relu. Okay, see, relu, 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 but only in the output there is sigmoid, because we need to squash the values, normalize the values between 0 and 1, and the sigmoid does it the best. Okay, this is how we basically do it for the autoencoder. Okay, and we compile it. Basically this is to start the backpropagation process that we were doing. So the loss is defined here as the mean square error, and the optimizer is Adam. Simple. Okay, this is the model training. So we are training it for 10 epochs. I explained epochs. I think epochs mean one epoch means basically one forward pass and one backward pass combined. Okay, too many epochs will it will basically lead to overfitting, because the model will train for too long. It will start memorizing the patterns. We don't want that. Some value between 5 and 15 usually is the sweet spot for these small data sets. Okay, so we took 10. Batch size is 256. Shuffle is equal to true. Basically what it will do is it will shuffle our data from time to time. So this basically prevents bias, and it selects a different subset of the data every time. Okay, this verbose is equal to 1. What it does is it shows the training per epoch later. Okay, I'll show it to you how it looks like. We then visualize the loss curve to get an idea how the training error and the testing error is looking like. Okay, this is how we have plotted it using matplotlib. Okay, then we did the reconstruction. So what we did was we are getting a reconstructed image back. So we are printing that reconstructed image in order to get an idea how our model has performed. Okay. And this was our little experiment where we are comparing it with PCA. So on this same data set, we have applied PCA, and then we have built this table to compare the PCA and the non-linear autoencoder. Of course, the autoencoder will perform slightly better. Okay. So this is the sample image. Okay. You see this loss per epoch, this loss value that we are getting per epoch wise. This is epoch 1 all the way up to epoch 10. So when we wrote in the code verbose is equal to 1, it allowed us to print these values. This verbose is equal to 1. Okay. So we print these values and we get the results. So this is it for the code. I guess everything is very clear. Okay, going back to the repo, you can see that this is the pipeline that we implemented. Everything has been done. Let's quickly go back to the comparison table. Okay, the math we have already discussed all of this. So this is how the training and validation loss or testing loss looks like. So it is closer to each other, meaning that the model is actually learning genuine structure. Okay, if it was varying very differently, then it wouldn't have been a very smooth model. So you can see how these values are slowly decreasing. Okay, this loss value is decreasing. Okay, you can read it, analyze it. Now the time complexity, very simple. Whenever we are talking about the time complexity in terms of these models, you only need to think about what we are doing. So at every epoch in the code, what is happening is that any sample is passing through all the layers, right? We have got, let's say this is the sample, first image of 784 pixels. It is passing through the encoder, the two layers of the encoder, then the latent layer, and then the decoder. Then we are getting the output. So that is what we try to implement here. Okay, so we are implementing it for all images 60,000, which is why we have got n. It is being done for e number of epochs, which is 10. What is the input dimension of each image? It is nothing but constant value 784, and h is basically the peak hidden width, the width that we implement here. This value, this is the peak hidden width. Okay, so this is what we are doing. So this is why the total time this is why the total time complexity scales out to be this is fine. It does not really blow up. So we still need to be careful with initializing these values, because that is what is depending upon our fast or slow training. Okay, space complexity, we only need to analyze what our model is even storing. So machine learning models, they usually store all the weight matrices. Okay, so we have basically got these weights here, to something about 200,000. Okay, so d into h to get the weights, and h into k to get the weights for the latent dimension. Okay, so this is the total weights. We don't want this value, we rather take this because this is the dominant term. Okay, this is very small by modern computation standards, because uh, modern computers basically allow us a lot of space that we can have for our weights. Okay, you can compare it with the PCA. This is what it looks like. So the PCA was obviously taking a lot more time. Okay, and this is quicker, especially if we have good GPU optimization. Okay, space is near about, and inference is also near about. If we compare it, we can see that the training time in case of the autoencoder is a lot higher, because a neural network is much more complicated, and since this is the non-linear case of the autoencoder, it is going to take lot time than a simple example of the PCA. Okay, inference latency is near about the same, and the reconstruction MSE is slightly better for the autoencoder in this case. Okay, now this is the reconstruction visualization. So this is how the original dataset images were looking like, and this is how the new or the reconstructed images are looking like. So they're all recognizable. That is what we wanted to check. 7, I can still say this is 7. This is 2, 1, 0, 4. Everything is still recognizable. It is not there is no harm done. But what has happened inside is that the underlying patterns have been captured, and basically all of the important data has been preserved. Okay. Now, the last thing, the failure cases. So, of course, all models have some sort of disadvantages. So, the failure case analysis, the first thing is about the latent dimension. So, we took the latent dimension and I discussed that the latent dimension k is nothing but a hyperparameter, right? So, I tried to discuss that this k here is nothing but a hyperparameter. See, it can have this value, this value, this value, this value, this value. Choosing it is very important because it basically impacts on how our model training is going to look like. So if we take a very high value, what will happen is that we will end up not really capturing anything. So you see, when we take a dimension which is large enough, the bottleneck or the constraint basically vanishes. The model will learn like a representation which is very close to the input itself. Reconstruction will be perfect, but there will be no useful structure that is being captured. If it is too small, then bottleneck is too tight, it is too aggressive. The model will not be interpretable enough because it will not be able to distinguish all the digit classes. Okay. You can look at the other ones as well. They are very basic to analyze. Okay, overfitting is also a risk because we are using a neural network. It can overfit like this. It is very easy to overfit, especially on small data sets. We need dropout to maybe regularize this. In this case, it was fine, but we need to be careful. A higher learning rate can also contribute to unstable training, so we need to take care of that as well. Okay. Key takeaways, you can read it, it's pretty simple. Okay, so the rest of the repo is open for you obviously to read. The link is in the description along with all of the articles that I mentioned. Okay, if you are unfamiliar about any of the concepts that were mentioned in this video, first read the article, then continue with the video. Okay, so that is, I think, it for the PCA along with everything that we have covered till now. That is it for the autoencoder that we did today. So this is over and I will see you tomorrow on day 14 with the credit card anomaly detection model using isolation forest. Okay, thank you.